What we want to do is implement the stuff we did last week in plain old scheme. Okay? So we want a system in which, well, in particular, we're worried about local state. So we want a system sort of like this. We have a class, and we have an instance, and another instance, and another class, and it has instances too. And there are global variables accessible to everybody. There are class variables associated to any instance of, accessible, to any instance of that class. And then there are instance variables that each one has on its own. And we want to see how that works. So the starting point is to notice that the substitution model that you've learned up to this point is not going to work once you can do set bang. Because if we take this 0 and substitute it in here, then the set bang isn't actually going to do any good. I'm sorry, if we substitute it in here in particular, the set bang, no matter what the set bang makes of that, this is going to just return 0 every single time. So we need a different model of evaluation that takes into account the possibility of changing the value of a variable and of a local variable and makes that possible. And okay, so this is our first definition of a counter, like the count class that we saw last time. You would send it a next message, and it would count up. And the way this works is that there's a global variable counter whose value is now 0. I can call, whoops, count, count, count. And every time I call count, it increases the value of that global variable. So this is just a straightforward use of set bang. And it shouldn't be a surprise to you that this works. But it's not good enough for that model that we want, in which we have private values of the counter, one for each instance of the class. So now, all right, this is the one that Jordy was writing. So here's an attempt to make a local value for each counter. There's still only one counter, but I'm making counter. I guess we have count and counter backwards. Instead of counter being a global variable, I'm going to make counter be local to this procedure. So that's the idea here. So now we're paying note, there is a global variable counter, which I can't get rid of. But forget about it, because we're not using it. So now, if I say count 1, I call count again, I still get 1. No matter how many times I call count, I'm going to get 1. Why is that? Well, every time we call count, it makes a brand new variable counter. And this is the use of let that we're accustomed to, where we create a variable just long enough to run the body of a procedure, and then that variable's gone. And the next time you call the procedure, it creates a brand new local variable. Well, that gives us local variables, but not persistent ones that we can use to remember the count from one call to the next. So here's the version that works. So first, let's load it. This has a different name, result, so we don't get confused with the counter global variable. Now if I say count, 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 you see that it does count, but result is not a global variable. It doesn't exist globally. And this works in a very strange way that isn't going to make any sense until we've been talking about it for a while. Namely, notice there's no parentheses around count here. So this is not a definition with an implicit lambda. The lambda that creates the count procedure is this one. And it comes inside the let that creates the variable which is going to be its local state variable. So that seems really weird. What does it mean to put a lambda inside a let? If you think of the procedure as just being the text of the lambda expression, which is how it worked in the scheme 1 interpreter that you saw a few weeks ago. Remember when you said lambda blah, 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 the value of that expression was just the lambda expression itself. And in that kind of world, because we were using the substitution model, in that kind of world, this doesn't make any sense because it's how do you find the result variable that isn't defined inside that lambda? And what's new in the environment model of evaluation, which is what this week is about, is that a procedure isn't just the stuff in the lambda expression. It's the stuff in the lambda expression plus some way of finding free variables in the lambda expression. What's a free variable? It's one that isn't a formal parameter of the lambda. So it's not defined inside the lambda, it comes from outside the lambda. Now, up to now, outside the lambda just meant global. And that's how it is actually in a lot of programming languages. All those C-like languages, C, C++, Java, they don't have the idea of procedures inside procedures. So there's just procedure local variables and global variables, and that's it. But we have the idea of a lambda expression inside another lambda expression. And that's what you're seeing here, because remember, a let is an abbreviation for a lambda expression and then a call to that procedure. So this thing that's up on the screen is equivalent to lambda of result and then lambda of nothing, set bang, blah, blah, blah. And call that with a 0 as its argument. Right? So the let means this. So in this lambda expression, the outer one, the green, no, I'm sorry, the outer one, the outer lambda expression, result is a formal parameter, so it's bound. So when you see a result in here, in this expression, it's bound. So we know what result means. It means this variable. But if you're only looking at the inner lambda, there's no way to know what result means if all you have is the lambda expression. So we're going to see later on, as we look at the details of the environment model, that a procedure is drawn like this. It has a left bubble and a right bubble. And the left bubble essentially points to the lambda expression. And the right bubble essentially points to bindings for the variables that are free in that lambda expression. So there's something here that says result equals 0. Okay, so both of these things are part of the procedure. And so when that procedure says set bang result plus 1, we know which result we mean, and we can turn that to a 1, and then next time turn it to a 2, and so on. Okay? So I know it isn't clear yet how we get here, but is it clear what we're trying to achieve? Right? That when you create that inner procedure, the one that's highlighted up there, it remembers where to find the value of result. Right? That's the goal.